good morning. This is the 15.1 video. And let me just warn you, I'm not feeling super great today, so probably won't be talking as loud as normal, but I'll do my best to be loud enough. But hopefully you'll be able to hear me. I don't know, it's just one of those days where I feel yuck. But anyway, 15.1 is obviously the first section in chapter 15. So they have an overview of the chapter here, and it just kind of gives you an idea of what we're going to be doing in the chapter and also where you can use it. So they have some applications here, science, engineering, etc. So you can read that later. And then here it tells you what we're going to be doing specifically in in 15.1. We're going to be, what's different about what we're going to be doing is we're going to be integrating over a curve instead of an interval. So in Calais, this is going back to Calais. In Calais, you had an integral over an interval from A to B, but now we're going to have an integral over a curve as opposed to an interval. And so these are called line integrals. They should really call them curve integrals because you can integrate over a line or a curve, but they call them line integrals. So here they tell you they're going to do the definition for space curves, which would be three-dimensional. But if you want to do it for two-dimensional, you would just assume that the z-coordinate is 0, and that makes it two-dimensional. So the three-dimensional case is just a more general case. So you're going to have a function of three variables. You're going to be trying to integrate over some curve C. It's going to be parameterized by a vector-valued function. So we've done that in Cal C. The vector-valued functions, you have functions of t in each of the components of a vector, and then you have the bounds on the t. And so you're going to be integrating with respect to arc length because like you have some curve, right, and the length of the curve would be arc length. Okay, so they talk about smooth in the definition. This is, sorry, last page was 828. This is page 829. They talk about smooth. So smooth is just that the v vector, which is the derivative of the r vector, it has to be continuous and never 0. So when they talk about smooth, just ask yourself, is my derivative continuous and never 0, and then it's smooth. Okay, so what you have here, this is the formula. It's actually down here too, but here's where they talk about it for the first time. So you're integrating over some curve, a function of three variables, with respect to arc length. That's what this ds is. The ds is with respect to arc length. And that's going to be, you're going to take your functions of t, and so this is like x of t, y of t, z of t, and you're going to plug those in to your function here, and it's going to change from a function of three variables to a function of one variable because it's just going to be t. And then anytime you do a change where you're changing from one coordinate system to another, there's an extra piece that's going to pop up. Remember in polar and cylindrical it was the r, spherical it was the rho squared sine phi. U substitutions it's 1 over the derivative of your u. But here the extra piece that's going to pop up is the magnitude of the velocity vector. So it's not a vector here, it's magnitude. So it's a scalar quantity. Magnitude of the velocity vector. So they have the formula for that here. Velocity vector is just the derivative of the r vector. So you take the derivatives of the individual component functions, square them, add them together, and take the square root since it's magnitude. So they talk about here kind of what's going on with this formula. So I'll let you read this later on your own, page 829. But basically, here's what's going on. I'm going to give you in my words. Here, this is the book's words. This is a function originally of three variables. If it was a function of three variables, it would have needed a triple integral, and you would have had to be doing it with dv, you know, dz, dy, dx, something like that. But what it's doing is it's taking it from a function of three variables, changing it to a function of one variable, and so now that it's a function of one variable, just a single integral will do it. And so it's getting you away from having to use multiple integrals, which is interesting. And so here they have the conditions. Again, it has to be smooth, which again means the derivative is continuous and not 0. And then this is changing it over. So in changing it over, they'll give you the bounds on the t usually, and if not, I'll tell you how to find them. Usually they'll give you the functions. If not, we'll talk about how to find them. So you're taking those functions and plugging them in to your original function, you're finding the extra piece, which is again the magnitude of the velocity vector, and then now it's a single variable t, so you're just integrating with respect to t. And so notice here, if your function is a 1, then what you're finding is just arc length. You're finding the length of a curve. So this is, I think, maybe your 4th formula now for arc length. You had, I think, 3, if I'm remembering correctly, in Cal B. So here's another one. Okay, sometimes you'll have a curve, this is page 830, like this, that's in 2 different pieces. And so you'll have to do it separately. And so what this is telling you is that you can do it in separate pieces. So if the overall curve is made up of individual curves, you can do the individual curves separately and add them all together. And then here's some more information about that. Again, I'll just let you read that on your own. This is page 830, so read that information on your own. Okay, so lastly, they have on page 832, I meant to highlight the whole box and I stopped, well, not the whole box. Anyway, whatever, I messed up here, so it should be this whole part highlighted. This is the geometric interpretation. So you can kind of think about the curve. The curve is in the xy plane here. The height is given by the z value. And so it tells you here, there's more information about it here, but this is kind of the Cliff Notes version of it here. It's the area of the part of the, I call it a fence. It looks like a curved fence. It's the area of the part of the fence here, like if you had, think about this like a fence and you were going to paint it, it would be like the area of that part of the fence. So that's but they talk more about it here, so I'll let you read that on your own. Page 832, geometric interpretation of line integrals. Okay, so here's not a lot of formulas in this section. These are 2 of the pieces that are in this formula. So the R, and here they have it as G, H, and K, just so it's not confused with this F. That's why they're not using F. That's why they start at G. But I a lot of times call it X of T, Y of T, Z of T, just so you can remember where the pieces go. Because I think originally when they defined these R's, earlier, I don't remember where it was, but in Cal C, I think they had this as F and G and H. And so it gets a little confusing because they're sort of redoing it now to keep this F from getting confused with an F up here. So I usually just call it X of T, Y of T, Z of T to keep it from being confusing. So that's what they have here, X and Y's and Z's. And so you can write it like this, which is the way the book did it. Or if you want it to match this formula, then you can write it. Notice it's a function of a single variable. It's just a T. So you can just write it with a prime. The only time you can use a prime is if you have a single variable, so there's no confusion about what you're taking the derivative with respect to. And so you have primes. Oh, in case I'm back in the sunroom. I don't know if you can tell, but I didn't put the tablecloth back on this table because I'm going to move this table upstairs and use a different table in here. So you can see, in case you're wondering what in the world's going on with my table, this is the table that's under the skylight that leaks, so that's why it looks so bad. So I'm going to get a different table, just is not put together yet. And look, no more blue floor. Isn't that exciting? My husband and I retiled the floor, so it's not blue, hooray! And there's the chocolate pudding painted deck. It wasn't actually chocolate pudding, but it sure did look like it. It's wet now, you can't tell, but it looks a lot better than it did. So slowly but surely improving the house. Very exciting. Nothing I can do about this table, I don't think. I don't know, maybe I can sand it, re-stain it. I don't know. That's a project for another day. Okay, let's look at some examples. Why are you not focusing? There we go. Okay, so in 1 through 8, they give you 8 vector equations, and then 8 kind of like, they're like the parametric curves. Parametric curves like we were doing, I don't remember when, but parametric curves is what these are. And they want you to match them up. Okay, so we're going to look at a few examples. Don't ruin the surprise and look at the answer. Okay, number 2. This is I plus j plus tk. My mind works better in component form, so I put it in component form. And this is for when t is -1 to 1. And so if t is -1, this would be 1, 1, -1. If t is 1, this would be 1, 1, 1, or it could be anything in between there. So it would look like this. The x has to be 1, the y has to be 1, and the z component is varying between 1 and -1. So that matched graph E. Okay, so I'm going to do number 4 next and have you try that by yourself. So try number 4. I don't want to slide my paper down and show you my picture. Okay, there's number 4 if you don't have your book handy. So try that one by yourself. See if you can figure out what it matches A through H. All right, so again in component form, this would be t, 0, 0. So the y is always 0, z is always 0. The x is changing, but it's staying between -1 and 1. So it would look like this. The x is staying between -1 and 1, y and z are always 0. That was graph E. All right, now for a slightly more challenging one. Try this one by yourself. It is number 8. Okay, try number 8 by yourself. All right, so for 8, you have 2 cosine t, 2 sine t, 0. T is staying between 0 and pi. So it would make this half circle, I guess. So the, wait, hold on. I think I did that wrong now that I'm looking at it. Because that z is not 0. I did that wrong. I thought I checked my answer. Hold on. Let me think about it for just a second. Why is my z there is between 0 and 2. So let me look at the rest of these. Are any of these? This one, my z stays 0 all of the time, but that doesn't stay between 0 and pi. Very strange. I'll have to think about this and I'll talk about it in class because I can't pause the video. I'm not using that app that lets me pause. But I was sure I checked my answer. But that doesn't seem right to me. Hold on, let me look again. Oh, I see. Okay. Okay, figured it out. Never mind. This was supposed to be a K. That makes so much more sense. This was supposed to be a K. So it should be, I'll fix it in my notes later. That should be K. That's 0. This makes so much more sense. I feel better now. Okay, I was wondering why that didn't work. Okay, so 2 cosine t, 0, 2 sine t. That was supposed to be a K. I miscopied it out of the book. That's why I always ask you guys in class when you ask me for about a problem that you're getting the wrong answer. That's why I always say, did you make sure you copied it out of the book right? Because that's usually the thing I do wrong, is copy it out of the book wrong. I'm horrible at copying stuff out of the book. Anyway, this makes more sense. Sorry. Notice here the y stays 0. So if the y stays 0, it's always in the xz plane because the y is 0 in the xz plane. And then you have this half of a circle because it's only 0 to pi. So it is h. Okay, that makes so much more sense. I feel so much better. All right, so you're going to do, for homework, all of the odd ones. And so again, you're just kind of matching them up based on what the graph would look like. So you're just looking at the characteristics for your t values. Okay, let's look next at the next group of problems. Evaluating line integrals over space curves. We're going to do number 12. Okay, so we're evaluating, this is the function over some curve. I put f of x, y, z because that's the general case. This obviously doesn't have a z, but it is three-dimensional because see, my r has a k component. So here my z is just 0. This is my r, and then my bounds on the t. So what you're going to have to do is you've got to get, they gave you the bounds on the t, that takes care of that. You've got to get the new function, and then you've got to get the extra piece that pops up when you change this to dt. So for the new function, this is x, this is y, this is z. So you've got this in place of x, this in place of y, this in place of z, and you're plugging them in up here. So it would be this. That is my dog making all kinds of racket. I don't know what she's doing. Okay, anyway, so square them, factor out the 16, cosine squared plus sine squared is 1, square root of 16, 4. So that would be my new function. It's a constant function, but my new function is 4. All right, now I need the extra piece, which is the magnitude of the velocity vector. So the velocity vector, you're just taking the derivative of these pieces. These are functions of a single variable, so you can just use prime. I'm taking the derivative of those. So let's move up here. Ugh, please never cooperate with me. All right, so here's the derivatives, and then that's a vector, obviously, so I'm going to do the magnitude of it. So square each of these pieces. I already showed the work for how this becomes 16, so I didn't do it again. 16 plus 9 is 25, square root of 25 is 5. So that's the extra piece that's going to pop up. So now our integral, it was a line integral. Now here's my bounds on the t, here's my function, here's my extra piece that pops up, and now it's a dt. So my thing that I'm integrating is just 20, which is obviously 20t. Plugging it in, I get 80 pi. Okay, so it's kind of like what you were doing and polar and cylindrical and etc. when you're changing from one coordinate system to the other. But here you're changing from a function of x, y, and z to a function of t using these vector value functions. All right, next is number 16. Notice, I think you have, I don't remember if you have 15 for homework or not. But anyway, if you do have 15 for homework, here's 15 down at the bottom, but the picture that goes with 15 is up here. Okay, so when you're doing that, I think that's a homework problem. Here's the problem, here's the picture. Okay, that's number 15. We're gonna do number 16. So notice in yours, number 15, you have 2 separate curves, but in mine, number 16, I have 3 separate curves. So I have to do each one of them individually. So they've specified here what the 3 curves are. They've given me my function, and I'm starting at the point 0, 0, 0, moving here, then here, then here, and so I'm ending at the point 1, 1, 1. So it's kind of a crazy path to get there, but it is what it is. Okay, so there's my function, there's my starting and stopping points, here's my 3 curves. So I'm gonna do these all 3 separately, so it's like 3 problems for the price of 1, hooray. So first, C1. So for C1, you need to find the function that corresponds to C1, and you need to find the extra piece, which would be the magnitude of the velocity vector. So for the function, C1, it has just 0 in the I, 0 in the J, T in the K, so it's 0, 0, T. So you're plugging that in here, 0 for X, 0 for Y, T for Z, so it's just negative T squared. And then for the velocity, that's just the derivative of this, so the derivative of this would just be 1K. Find the magnitude, it's 1. So that's C1. All right, C2, same idea, different pieces. 0 in the I, T in the J, 1 in the K, so it's 0, T, 1. You're plugging that in up here. 0 for the X, 1, what was the, oh, no, just kidding, T. Couldn't see. T for the Y, 1 for the Z. So you're plugging all that in, and it simplifies down to square root of T minus 1. Then you're doing the velocity, which is the derivative. You're here at C2, so the derivative would be 1 in the J, 0 in the K, so it's just 1J. Magnitude is 1, and I do the same thing for C3. C3, though, notice it's T in the I, 1 in the J, 1 in the K, so it's T1, 1. Plug it into the function. The new function is T. Find the derivative, and the magnitude is 1. All right, so let's put this all together now. So notice I did it originally as 3 separate pieces. I've got curve 1, here's my function, here's my extra piece. Curve 2, here's my function, here's my extra piece. Curve 3, here's my function, here's my extra piece. So my bounds are 0 to 1 because, hold on, let me show you. They didn't tell me that. I didn't show the work because this one's pretty easy, but you're starting at this point and you're stopping at this point. And so what you're asking yourself is what t value does this correspond to? And what t value does this correspond to? So the easiest one to plug them into, wait, did they give me that? Oh, just kidding, they gave them to me, sorry. I'll show you on another one. Here they did give them to me right here on the side. So 0 to 1. I'll show you on another one. But anyway, basically you're just finding the t value that corresponds to these points. We've done that before, but I'll wait and show you on another one. Okay, so notice here they all have the same bounds. They're all dt's. So in that case, you can put them together. So put them together to make one integral. And then I integrated, and then I plugged in, simplifies down to negative 1/6. All right. So next group of problems, line integrals over plane curves. So these are now 2-dimensional, the ones we were doing. Notice this was line integrals over space curves, that's 3-dimensional. Line integrals over plane curves is 2-dimensional. So same process, it just doesn't have any z components here. So we're going to do number 20, and I have 2 different parts, part A and part B. So part A is the straight line, x equals t, y equals 4t from 0, 0 to 1, 4. So here they didn't give you the bounds on the t, so we'll talk about how to find the bounds on the t. Okay, so my function, my r, it has x of t in the I, y of t in the j. So this would be the x of t, this would be the y of t, so it's just t in the I, 4t in the j. So I went ahead and found my velocity vector and then the magnitude of that. So that's going to be my extra piece that I use when I set up the integral. Okay. Now I got to figure out my t's. So here I did show the work. Okay, so at 0, 0, you replace, okay, so this is x is 0, this is y is 0. So you go back up here, put a 0 in for the x, put a 0 in for the y. So you have 0 equals t, 0 equals 4t together. That tells you that t has to be 0. And then at 1, 4, you put 1 in place of the x, you put 4 in place of the y, together, that tells you t is 1. So this one, the t is between 0 and 1. So that's how you figure it out if they didn't give it to you. You're just plugging them in to solve for them. All right, so now I have to change over my function. So my original function was up here, and so I have x is t, y is 4t, so my new function ends up being 3 square roots of t. So here's my extra piece, here's my bounds, here's my new function, put them all together, bounds, function, extra piece, and those are the 3 pieces that you're always going to have to do. The bounds usually they give you, but here we talked about how to find it, the new function, and the extra piece. Those are the three pieces, and it's the same as like what you were doing in polar and cylindrical and etc. Except, well, maybe more for the UV stuff. In the 14.8, in the UV, you had to find the new region to get the bounds. You had to find the new function. You had to find the extra piece, which was the Jacobian. So it's the same thing here. So the 3 pieces are bounds, function, extra piece. But here the extra piece does not come from the Jacobian. Here the extra piece comes from the magnitude of the velocity vector. All right, so here's my new bounds, my function, my extra piece. And then hold on. Oh, just kidding, it was up here. I was like, how is that my extra piece? Okay, sorry, this was it. My bounds, my function, my extra piece. That makes more sense. I told you I'm not feeling very good, so probably not gonna make a whole lot of sense today. I'm sorry, I'm trying to do the best I can. All right, so here I just moved these out because these are constants. Here's my thing I'm integrating. So I integrated, plugged in, and it's 2 square roots of 17. All right, part B. Part B is a little more complicated, so I'm going to help you get started on it, and then I'm going to have you try it by yourself. So notice in part B you have 2 different curves. So you have curve 1 and you have curve 2, and they're both line segments. So you do know how to do this. You may not know that you know how to do this, but you learned how to do this in Cal B, and we've talked about it again in Cal C. So I'm going to get you started, and then I'm going to let you see that you do know how to do this, and then I'll let you finish it by yourself. So let's start with C1. C1 is the line from 0, 0 to 1, 1. So this is something that you would have done in 11.5 in Cal B, and then we did it again in Cal C. It's the parametric equations for the line. So you're trying to find the parametric equations for the line. So hold on, don't look. Okay, that's C2, I had to cover it up. Okay, don't look at C2, I'm gonna have you try it by yourself. So here's C1, you have from 0, 0 to 1, 0. So you're gonna find the vector between those 2 points. So it's terminal minus initial. So terminal minus initial, that gives you the vector. And then your parametric equations, you have, hold on. Okay, you have the point x naught plus the x component of the vector v1, and then the point y naught and the y coordinate of the vector, so it'd be v2. Well, I'm calling everything here subscripts 1 because this is curve 1, and over here I'm calling them subscripts 2 because it's curve 2. So sorry, that's getting a little confusing with all the subscripts. The v1 here is my whole vector. Anyway, so the parametric equations for this line are x1 equals t, y1 equals 0. I don't know if we talked about this in Cal C, but when you do parametric equations for the line, the first point always corresponds to t equals 0, and the second point always corresponds to t equals 1. And so this would be between 0 and 1 for the t, so you don't have to solve for it. Okay, now that I got you started, you do C2 by yourself, and then this is going to be like that number 16 that I did where you have the 2 separate integrals. You have one for curve 1 and one for curve 2, and then if you can put them together. I think this one's going to need a U substitution so on one of the integrals, so you're not going to want to put them together. But so right now, pause the video, try this one by yourself, and then come back and check your answer. All right, so C2, here we go. C2, here's the 2 points. I do this. Notice I'm calling everything subscripts 2 here. Terminal minus initial, so here's my vector. Plug in the point, plug in the vector. Here's my parametric equations. So for my R's, this is my R for curve 1. Again, t is between 0 and 1. Here's my R for curve 2. T between 0 and 1. Find my extra pieces. So velocity, magnitude. I didn't show the work for the magnitude here because we did that before several times. I did show the work here. Velocity, magnitude. So that magnitude is 2. Now you need the new function. So here was the original function. So you're just plugging in your x and y. So here This was t in the I, 0 in the j, so it's t0. Plugging that in simplifies to this new function. Here it was 1 in the I, 2t in the j. So you have a plug 1 in for x, 2t in for y. So this is your function. All right, so now putting it all together. Here's curve 1, the new bounds, the new function, the extra piece. Curve 2, the new bounds, the new function, the extra piece. This one needs a u substitution, so it's just easier to keep them separate. These are very basic Calais integrals, so I'm just going to show these to you. So your answer should have been in either form. So check your answer here, and then I'll show you the work. One of these two should have been your answer. All right, so here's the work in case that's not what you got. This one, it's just a regular integral, so you just get 2/3 for that one. This one, you need a u substitution, so here's where I did the u substitution. The 2 and the 4 become a 1/2. Integrate, that cancels down to 1/3. Plug back in for my u. And 5 to the 3/2 is square root of 5 times square root of 5 times square root of 5, which is 5 square roots of 5. Distribute the 1/3, and then put this piece together with this piece, and you get this. All right, so that was number 20. Let's try another one. This one's a little confusing, so I'm going to get you started on it and let you finish it on your own. Page 834, number 30. I think this is the last one. I don't know if that helps to know it's the last one, but anyway, I don't have any good stories for you today. I don't feel good, so it's hard to come up with good stories. I don't know what I'm going to put for to see if you were paying attention on this video. I got nothing. Sorry. Okay, here's my function. Here's my curve. First quadrant starting at this point, moving to this point. So this is obviously a circle centered at the origin, radius 2. So I drew the whole thing. I drew the whole circle. But it's starting here at 0, 2, and then it's moving to square root of 2, square root of 2, which corresponds to pi over 2. So normally, I mean not pi over 2, pi over 4. It corresponds to pi over 4. Normally at pi over 4 you have square root of 2 over square root of 2, but since this is a circle of radius 2, that's why it's square root of 2, square root of 2. What did I say the first time? Okay, I don't know what I just said, but in the unit circle, it would have been square root of 2 over 2, square root of 2 over 2 in the unit circle at pi over 4. This is not the unit circle because this is radius 2. So since it's radius 2, instead of square root of 2 over 2 and square root of 2 over 2, it's just square root of 2 and square root of 2. I don't know if that helps, but that's why it's different, because this is not the unit circle. The unit circle is radius 1, this is radius 2. All right, so for your curve, you need to get this. There's a chipmunk. Say hi, chipmunk. There he is. I have crazy spastic chipmunks that run across my deck on a regular basis. But that creepy cat that used to stalk the chipmunks hasn't been back since that day I made the video about him. Oh well. Anyway, back to math. I don't know if you remember this from parametric equations. This is backwards from the way you were doing it in parametric equations. In parametric equations, before you would, I think, start with the t's and go to the x and y's, but now we're starting with the x and y's and going to the t's. But anyway, whenever you have this, it is the same thing as, because it's equal to 4. 4 cosine squared plus 4 sine squared, because notice here you could factor out the 4, cosine squared plus sine squared is 1, so that would just be 4. And then 4 cosine squared is the same thing as 2 cosine squared, and this is 2 sine squared. So for this, you have two choices. You can either, choice number 1, have this be the x and this be the y, or choice number 2, have this be the x and this be the y. And the difference is where they start. They start in different places. So you have to see which one works for you. So I checked them both. For choice number 1, this is obviously not the one that works, hence the big X in the margin. If you try it this way, what is on the paper? This curve starts at, when t is 0 is where it's starting. When t is 0, it starts at 2, 0, but I need to start at 0, 2. So this one's not going to work for me. But if I try the other one, when t is 0, starts at 0, 2, and then it moves to this point when t is pi over 4. And so this is the one I want to have with the x being sine and the y being cosine. So you could have done it in either order. Either one of those could be x or y. It just depends on where you want it to start as to which one you're going to choose. Okay, so now that you have your r, this is the r, I'm going to have you finish this one on your own. So pause the video, try this one by yourself, and then we'll talk about it. Okay, so here's some of the work. Here's my r. I'm going to find my velocity vector, find the magnitude of it, simplifies down to 2, so that's my extra piece. I've got to find my new function. Here was my original function, x squared minus y. So I'm plugging this in for x and this in for y. So here's my new function. So this line integral, here's the new bounds, the new function, the extra piece. Distribute the two, or you can put it out front, it doesn't really matter. You can't integrate sine squared, so you have to use this identity to fix it. 8 times 1/2 becomes 4. Distribute the 4, and you have this. So this is actually what I'm going to integrate. All right, so integrating, plugging in 0 and pi over 4. When you plug in 0, this is 0. Sine of 0 is 0. Sine of 0 is 0. So all of those pieces just become 0. I did check it. I just didn't show the work. So this is the way I had my answer. This is the way the book had the answer. I don't know why that's wet. It wasn't in here under the skylights. Who knows what happened there. But anyway, that should be the final answer. Okay, so this is all from the 15.1 video. Again, I apologize for all my mistakes and lack of enthusiasm and no fascinating stories. Sorry. But if you have any questions, just send me an email.